In this video, we are going to demonstrate how we can use decision trees and decision zone maps to make defensible decisions. Bank Zoko grants a $20 million loan to a cement factory. The factory gets into financial difficulties. The bank takes over and appoints a consultant to find some solutions. And of course, any proposal must be approved by the bank's board. Hence, it must be defensible. The consultant comes back with two recommendations. Option 1, invest an additional $8 million. And he says the likelihood of a successful turnaround is about 65%. The benefits of that would be a recovery of the loan plus any new investment, plus another $5 million bonus. Of course, if not successful, there would be a total loss with bankruptcy. Under bankruptcy, they might be able to sell the equipment for $8 million. If not, they might recoup just $4 million. Now, option 2 is do not invest anything. But the consequences could be serious. First, there's a 40% probability that the government might forcibly acquire the facility to provide employment to the local township. He estimates that there is a 35% chance of success and the government would pay the debt, but they have no obligations if they fail. Now, if that doesn't come through, there's a 30% probability that a competitor might acquire your facility for $5 million. Now, with them, there's a very high success rate of 80% because they know their business. Now, they will pay the balance debt plus a $15 million bonus.
Here again, no obligations if they fail. Now, of course, if neither of these were to happen, the bank would be forced to go into bankruptcy under the same terms. Question is, what should the bank do? Here we have a problem with two options and with uncertainty of data and information. It would be a stretch to think that common sense and discussions is a way to arrive at a defensible decision. This type of problem must be simulated.
The first thing we must do is sketch the decision tree. So let's start with our decision node, D0. We have the option of investing or not invest. If we invest, there is a probability that we might recover all our money, which is success. And of course, failure would be bankruptcy. And then we have the high salvage value and the low salvage value. Now, if you do not invest, we have the three options. A competitor acquires, the government acquires, or we are forced into bankruptcy. And in each case, we have the potential for success or failure. So this is actually the sketch. Now we use this sketch to develop the Excel model. Now we invoke our Excel app. Here is the master model. And what we do is we reproduce this diagram in Excel. And it's very easy, as you saw before. We start with our initial node D0. And the next two are probability nodes. Create one probability and another probability node. 3 legs, so we need to create an extra leg here. All of them are probability nodes. So now we have 3 branches with the associated terminal nodes. And here we have to create one more probability node. So here is the diagram. In the interest of time, I've already labeled the entire tree. So let's take a look at that. So here we have the labels: invest, do not invest, investment fails, competitor has acquired. And if all else fails, we have to file for bankruptcy, similar to this scenario. Then I've also inserted the terminal values. So this is our decision tree for this scenario. And under this scenario of 0.65 and 0.4, it's an investment decision. Please know that this param 1 and param 2 are governed by the scroll bars. If I change the scroll bar, it becomes 55. You can see. If I go down, the decision changes. The next thing is to see how we can build a decision zone map. So let's go to the zone map here. And here I have already built the zone map. In one of the earlier videos, we showed you how to do a zone map. So now we have the zone map. But what does the zone map mean to us? So let's take a look at that.
This line is known as the demarcation line. It could also be a curve, but in this case it is a straight line. And this diamond is known as a diamond pointer, and it represents our initial assumptions of 65% of probability of success and the 40% probability of government acquisition.
What is important to note is the horizontal distance and the vertical distance of the diamond pointer from the demarcation line. Under this scenario, the decision is to invest. But if the diamond pointer crosses to this side, the decision is do not invest. And let's demonstrate that. There you are, change to do not invest. Go back to here. The distance from A to B is the degree of freedom or latitude. What it tells us is, though we started at 65% up here, till we get to about 48%, there is no risk for us. So if the consultant had said the likelihood of success is 50%, we would still have a decision to invest, because it's only at 48% that we should be concerned with our original decision. Likewise, when the probability of government acquisition goes from C to D, until that probability hits about 74%, we should continue to invest.
This D-zone map also provides a very important piece of information. Note that at the 65% probability of success, the diamond pointer does not intersect the demarcation line. This means that this decision to invest is independent of the probability of government acquisition at the original assumption of 65% probability of success of the investment. There is no way that anyone could have arrived at this decision without something like a D-zone map.
So please note that the horizontal and vertical distances of the diamond from the demarcation line provides management necessary information to evaluate the sensitivity of our original assumptions.